hope the computer doesn't crash this time. Okay, so for question 15 though, we had mentioned that the entries in the matrix A are uniquely derived from the coefficients of the linear transformation on the basis of Fm1. So this will go here, here, and so on. So really what we have is like this, I think, and so on. Okay, so what we got is this. Now, of course, for arbitrary vector which is in Fn1, it can be expressed as a linear combination of the standard unit basis, or the standard basis in Fn1. The linear transformation over the standard basis, the linear transformation of the vector is the same as the linear transformation broken down into transformations over the standard basis times some fixed coefficients. So then what we'll have is this. Actually, it's probably better for me to write it in more concise notation so that we can save some space. Also, it's a bit annoying to manage, but I think I can do it. What the heck? Why don't I just write everything together? So if I write everything together like this is exactly what you would want. Yeah, I think this is exactly. But looking at it from the matrix transformation side, on matrix A times a vector, you can decompose this, but actually you shouldn't have to do that, because I mean, this being written as this in Fm1 is the same as saying this is the same as this vector. And then what you can do is then notice that let's see, how can I do this in a good way? So this is equal to C1 times this once again, and so on, right? And the reason is because when you multiply this by this, only the first element gets carried into the top. Whenever you multiply a row, only the first element gets multiplied by this C1, right? So you have that in the first, but you also have C2 C2 like this, right? And so on. Yeah, sorry, I'm really starting to run out of space. But let me think. How can I make this better? Oh geez, okay, this is crowding my thoughts. I'm not quite able to sync with so many things at once. There's too many things going on. Okay, I think this should be the final form for this, and we want to show that these two are the same. Well, I mean, I have a sneaky suspicion that you can just place the CJ here like this, and you can interchange. Oh wait, that's a okay, there's a big difference here. No. No, the result should be in terms of okay, I see. The I and M are okay. There's something going on. It's kind of weird. So I can associate this. Okay, now these two are the same. Okay. This interchange is possible because I is not related to this J at all, so it's not affected by this iteration. So I can move it outside. It does not matter. Yeah. So in fact, I've shown that for any arbitrary t, you can find an a by to represent that t, so that t of x is equal to x for every x. So it's fine. Suppose we use finite dimensional. T is an operator. Put that t is a scalar multiplied in the okay. Oof, okay. Yeah, no, that's rough. Okay. So if st equals to ts for every s in the linear operator space, then t is some multiple of the identity. So let's try to show this way, and then we'll show the other way. Okay. I think that might be decent to do. It's gonna be annoying though. I don't like the looks of this. Actually, the other way might be easier. So I can gain some insight first by going the other way. So if t is lambda I, then what does that mean? Well, that means we got this. As just equal to yeah, something stupid like this. Well, that doesn't seem too bad. The other way is like the really bad thing. Right, so you want to know that if s t is equal to ts for all s, this is going to be annoying as heck. Okay. So let's say t is not for any, so anytime I'm lost, I think contradiction is a good place to start. Let's say it's not equal to lambda times at the identity for any such lambda. Let's see if there's a way to break it. So then t of v is not equal to lambda v for some v. Then s of t of that v, let's say, so s of lambda. How can I exploit this? Is there even a way to exploit this? So I wonder what made it so that if t is a okay, hold on. If t is a multiple of the identity, that this works so well, because I sort of like, obviously it's identity, so it works, but there's something weird about it. Well, there's this slightly interesting aspect where anytime that s is injective, so must t, because if s is injective, then t composes s, or no, sorry, that's no, I can't go that way. No. Yeah, no, it is actually difficult. No. I can't believe I thought about this before. Like, at some point I actually knew how to do these questions, and now I'm coming back to it and I'm feeling quite lost once again. This is quite tragic. Well, I guess this is what you call learning, right? It's not that junk where you pretend you learned something in school for an exam. I'm tired of that. Yeah, that's exactly what I've been doing, cramming for an exam. Not a great look, honestly. But, I mean, what can you do? You only have 10 to 12 hours in a day where you can realistically study, and if, let's be real, maybe 5 or 6 of those are really top-notch studying. The rest is like filler. You might get some stuff done during that time, but it's pretty passive. It's just a mountain upon mountains of work that you don't really understand nor care about. So I want to start caring about this in particular. Okay, let's see. Well, how can I construct S so as to break this? So that ST is not equal to TS. How can I construct such an S? Right. So if we let T of V equals to W, let's say S of W equals to question mark. So V equals to question mark. We don't know. We don't know any of these things, okay? So let's say let S of V equals to G, I don't know, something. And T of G. Or better, why not just make S of V 0, then T of 0. This is forced to be 0, right? This not equals 0. Well, I don't know that. Okay, let me think. 0 for some reason. Otherwise, oh, apparently, yeah, no, TV equals 0 works, but it's not what we're trying to do here. And then what we have here is like T of, for this V, we have T of V is W. And we'll S of W be 0. So S equals T is 0. But here I just have to justify that indeed, like, this is a valid linear transformation S. So how do I do that, right? Construct rest of S. So what I want to do is set the rest of it equal to 0, so the rest of S equal to 0 to save me some trouble. But what I could do is say, well, base of V equals to V1, Vn minus 1. So extend to a full basis. Now S of Vi equals 0 for I is greater than 1. And then what I know is that this is perfectly linear. This is perfectly linear. I define on V, that's fine. But what we know to be a fact, perhaps, is that S of W, but W is not a multiple of V. So, in fact, it must be written as a linear combination of some other elements, potentially plus v, but that means that, you know, w can be written as, let's say, cv plus 2, where 1 ci. So one of these guys, this is not 0, right? It's not 0, which means that this part gets mapped to 0 entirely. But in this part gets mapped to C V. Oh. Okay, is that a problem? I think it is, because what if it has some component which is no, okay, no, this doesn't work. Oh, okay, I thought that was close there, but I guess not. Well, what if S of V is 0? Right, then T of S of V is 0. But then S of T of V, W. This is not equal to 0. Because if this is equal to 0, then W equals to CV. But we got the contradiction here. So we know that S of W equals to S CV plus S of this. And we just define that S of V equals to VI for all I between 1 and n. So this is S of something not 0. Equals to CV plus V prime. And this is just equal to W prime, which is currently not equal to 0. So we're done. If we manage to construct an S such that for every T where this does not hold true, the ST does not equal to TS on the specific V. Okay, that was pretty nefarious the way I designed that, but I mean, when you get a tough question like this, what are you gonna do? Right? I'm not Terence Tao. I don't know the bigger picture all of the time. You gotta move forward sometimes, even if it's like a pretty forced solution like that. Well, maybe there's something I can see from this, right? Because, right, like, S can force something to be 0, but since T of that thing doesn't go back to the same constant multiple of this vector, then S of this thing's outside the other part of the spanning list will be not 0, I guess. So T can squash, so I guess S can squash some bits down to 0, map some V to 0. Then T of V doesn't necessarily, it brings you to some V and also some other stuff. Which S will bring this V to 0, but this will not bring to 0. Well, I guess pictorially that's how you could understand it, but I don't know. Still pretty flimsy argument, I think. In fact, like T being a scalar multiple identity is very strong. It's much stronger than perhaps even invertible. So